Hi everybody. Today we will finish chapter 7. We're talking a lot about alkenes here, and in the previous lecture I introduced what an alkene is, and we went through a lot of nomenclature, and especially talking about how there's stereochemistry for alkenes, not just cis and trans for disubstituted alkenes, for example, but if you have a trisubstituted or tetrasubstituted alkene, we talked about the EZ nomenclature. So you have to make sure you know how to do that whenever you do any naming problem. If you have a double bond that has stereochemistry, you must indicate it. And it's always the safest option to use EZ rather than cis and trans. Sometimes students make the mistake of using cis and trans for a trisubstituted alkene, and that doesn't work because we're not knowing what you're exactly referring to. For disubstituted, it's easy. So today I'm going to wrap up about alkenes and just really talking about their properties. The next chapter I'll follow up on a lot more about each of the reactions that you'll learn for alkenes. So the next chapter is very reaction heavy, and you're getting deeper and deeper into organic chemistry. Today, like I said, we're doing more properties. We are going to review over electrophilic addition, which is the mechanism that alkenes undergo. So you'll get some review in this chapter as well, which we're starting you off nice and slow. Okay? So what I want to first talk about are the stability of alkenes. And it is found, based on thermodynamic experiments and calculations, that cis alkenes are less stable than trans alkenes. We can see this by this isomerization reaction, where if we have a trans alkene and we were to add a strong acid catalyst, then we could see equilibrium of the trans and cis isomer, where the trans isomer dominates at approximately a 76% yield, and then the cis isomer is about 24%. And in the next slide, I'm going to show you a different reaction that's easier to measure the stability of alkenes, and that's going to be using a reaction called hydrogenation. And you're going to learn this in great detail in Chapter 8. All the ins and outs of hydrogenation reactions. It's a very simple reaction, and we usually use that to help us to determine the stability of alkenes. And it's found that the less stable isomer is higher in energy once we do our calculations, like you'll see. But before I move on, why do you think the cis alkene, just looking at its structure, is more unstable than the trans alkene? Well, hopefully based on the knowledge you've already acquired of some structure-property relationships, you may look at the methyl groups, for example, here, and notice that these methyl groups are a lot closer to each other than those methyl groups that are in the trans position here. And so what kind of strain are we dealing with here when they are on the same side? Good. We are dealing with steric strain. Okay, so that's why cis alkenes are not as stable as their trans alkene. It's because the larger substituents are on the same side of the double bond. So if I were to ask you on an exam which is more stable and you forgot, oh man, it's 50-50, I know. It could either be trans or cis, but which one is it? Always try to think back to the basics. If something is more stable, what makes it more stable? Think about sterics and any kind of strain energy that you've learned already in the previous chapters. Okay? Now, I said that we know this experimentally, specifically using the hydrogenation reaction. And I first have to show you what this hydrogenation reaction is. Basically, you take an alkene and you add hydrogen and a catalyst. So palladium is going to act as a catalyst, and you're going to learn about different catalysts that you can use for hydrogenation. It doesn't have to just be palladium. It can be platinum. Usually it's a transition metal catalyst that helps us do it. And catalysts help to speed up the reaction. And in the laboratory, this is a relatively easy, fun reaction to do. You just basically get your round bottom flask with your alkene, and you add your catalyst to it. I used palladium on carbon, and then you have a hydrogen balloon, and then it reacts overnight. So it's a pretty easy reaction to do. You just have to be careful because hydrogen is flammable. So if you ever do work with it, be safe about it. You'll notice that this is cis-2-butene, and we did a hydrogenation reaction here. And if you do hydrogenation reactions to trans-2-butene and to cis-2-butene, you get the same product, right? So if we were to show the energy diagram for this particular reaction, the product of both reactions would end up being the same energy for butane, for example. And so when we measure the free energy difference between the products and the reactants, the free energy that's given off, right? Or actually we're measuring the heat energy that's given off here. We see that there's a larger difference between the cis and the trans. And therefore, the more stable alkene gives off less heat. Okay? So in reality, I know I'm showing delta G here, but when you're doing this particular experiment, you're measuring the heat energy. And this is an exothermic reaction, so the heat energy released. And when we talk about heat energy, it's delta H, which is a thermodynamic term within Gibbs free energy. Both are exergonic and exothermic reactions. Okay? And so we find that the trans alkene gives off less heat, and therefore its starting material must have been lower in energy and more stable. So starting material must be lower in energy and more stable. Okay? Okay, so I just told you that trans is more stable than cis, right? But what happens if you have a tri-substituted or a tetra-substituted alkene? What is the order of stability for those alkenes? And the order is that the more substituted the alkene, the more stable. Okay? So I'll write that down here before moving on to the next slide. And this is important. The more substituted the alkene, the more stable. Okay. The reason for this is twofold. Okay. One is based on this property called hyperconjugation, and make sure you understand, not just learn the definition, but you understand what hyperconjugation means. I find that students struggle with this particular vocabulary word and just understanding, what does it mean in organic chemistry and how is it helpful. So make sure you fully understand it. You can talk it out with a friend or talk it out with me. So what is hyperconjugation? Basically, it is the stabilizing interaction between filled pi orbital and a neighboring filled CH sigma bond on a substituent. The more substituents there are, the greater the stabilization of the alkene. Okay? So what we're saying here is, for example, let's just say I had this guy here, right? Ethylene versus this one here. Okay, now based on what I told you on the previous slide, which one is more stable? The tetra-substituted alkene, good. This one is more stable. Why is that? Well, you have to think back on molecular orbital theory. Kind of like a hybrid. You can use valence bond theory to help you out with this, but really it's all about molecular orbital theory. And for electrons to be, let's go back to resonance. Okay, so we said that resonance is the delocalization of the pi electrons in those p orbitals, right? And I said that the more resonance structures you have, the more stable that particular compound is. And the reason why that is because the electrons are spread out over more nuclei, right? Electrons are attracted to nuclei because they're positively charged. So they want to spread out over a molecule if it can do that. It doesn't want to just be in a local position, okay? And so what we mean by hyperconjugation is that, for example, here we have these p orbitals that are above and below the internuclear axes. And I'm kind of using valence bond theory here, so I'm talking about p orbitals rather than one big molecular orbital shown here. But if we just have hydrogen there, what is hydrogen's, for example, atomic orbital? It's just a 1s. It's like a tiny little 1s orbital, and they're spherical in shape, and it's just, there's not much to it, right? There's not a lot of volume to it, right? Whereas if I have carbon over here, for example, what is the hybridization of each of those carbon atoms? These carbon atoms are sp3 hybridized, which means they have bigger orbitals, right? There's more volume to it. So when we combine all these big orbitals to make bonding molecular orbitals, the electrons have more space to kind of move around, right? And so we call that, in a sense, hyperconjugations. The neighboring orbitals are helping to stabilize those pi orbitals that are in the center where the alkene is located. Okay? So the more substituents you have on your double bond, like alkyl groups, methyls and ethyls and isopropyls, the more stabilizing they are to that particular alkene. Okay? So like I said, it's you might have to rewatch this slide over and over, read the textbook. It's a really good explanation. Talk about it with me in the classroom when we're working on a work session, and I hope you'll begin to understand it. Another reason has to do with the fact that a bond between, for example, an sp2 and an sp3 carbon is stronger than, for example, a bond between an sp2 and a 1s hydrogen. So it's all to do with bond strength as well that helps with stability. Okay? So I'll write that here. A bond between an sp2 and sp3 carbon, or carbons, is stronger than a bond between sp3 or sp2 and 1s, for example, or even stronger than sp3 and sp3. So it has to do with bond strength as well. Okay? So just to review, the more substitute the alkene, the more stable. And if you're dealing with disubstitute alkenes, trans is more stable than sets. Okay, so that just kind of summarizes due to hyperconjugation and also due to bond strengths. Now, in the last lecture, or last chapter, I introduced electrophilic addition to you. I want to do it again. Okay, and like I said, I want you to understand the pattern of this mechanism, not just memorize it, but understand how to derive it on your own, so that when you start to learn all these different reactions, you're not memorizing their products. You're not memorizing their stereochemistry or their regiochemistry, which I'll get into. You actually understand it, you can derive it on your own, so there's no memorization. Okay, I know what my nucleophile is, I know what my electrophile is, I know how to react them. And I find that the students are the most successful in my class, all the way up till the end. Don't memorize the products of reactions, but in fact derive their mechanisms for each of the reactions while they're taking a test, for example. And so by deriving the mechanism, I think they're pretty sure of themselves. Like, I know I got this. I know I got this product, or I got two products here. Okay? So it may seem redundant right now, but I want to be repetitive so you see the pattern, and you can use that pattern to apply it to more complicated mechanisms. All right? I'm going to do color coding with my mechanisms so we're consistent. I always have my starting nucleophile in red, my starting electrophile in blue, and my electrons moving in green, okay, or at least the arrow pushing is in green, new bonds are formed in green, and all that sort of stuff. So you'll see that consistency there. So it's always good to have a red, blue, and green pen nearby when I'm going through all these mechanisms and introducing new mechanisms to you. And, make sure another piece of advice that I found, my more successful students derive their mechanisms on their own. Like, they'll watch my lectures online, they'll write everything down, and then for the mechanisms, they'll go and try to derive them by themselves without looking at it. Say, like, did I really understand what was happening here? Okay? So just my words of wisdom for you. I hope that you take them, and this makes a lot of sense to you. So, I always start off with my nucleophile in red. The alkene, remember, always acts as the nucleophile. So I'm going to start off with this alkene, for example. If you want to practice mechanisms, you can always come up with your own starting material. You'll get more sophisticated, and you'll make it fun. You'll practice with your friends. So just letting you know, you don't always have to practice with the same starting material that I give you. You can make up your own. See if you make it challenging. I'm going to react it with HBr. I'm actually going to draw the full Lewis dot structure of HBr. So I've drawn that bond in the middle and then the lone pairs. Okay. And I will show the electron arrow pushing in green. Remind you that this is your nucleophile and this is your electrophile. And you always draw electrons from nucleophile to electrophile in polar mechanisms. Always. Okay? So the electron-rich area for an alkene is the double bond. Remember that this pi bond breaks and grabs this hydrogen because the hydrogen is partial positive and the bromine is partial negative. Right? But remember when we practiced this in the last chapter, you can't just pull off a proton and leave bonding electrons dangling there. They have to become non-bonding electrons. So they become localized onto the bromine there. Okay? Don't forget the second arrow. Okay? Don't make that silly mistake. Let's go ahead and draw the intermediate. Now I'm going to have to help you with this here. I specifically chose an asymmetrical starting material to make a point later on. I'll explain more why it does this. But the hydrogen goes on to the less substituted side. So these two hydrogens stayed the same. And there's a new bond here. So this hydrogen went on the less substituted side. And that's that blue hydrogen. Now, because that pi bond broke, those two electrons grabbed on to the blue hydrogen, formed a new bond. What kind of formal charge are you left with? You're left with a +1 formal charge. Good. And the name of this intermediate is a what? It's a carbocation. So for electrophilic addition, we always form a carbocation intermediate. Good. And talk yourself through it. Don't be shy. Talk out loud. Walk through this with me and be actively engaged in learning, okay? Now, I'll explain why the carbocation goes on the more substituted side. You may already be thinking ahead and saying, okay, more substitute alkenes are more stable, more substituted carbocations are more stable. I'll explain that in a little bit. We also created a bromide anion, so I kind of write that here. And a lot of times students kind of worry about, well, this is an intermediate too, and true it is. Why is it not in the brackets? If you put it in the brackets, that's fine. Normally, I usually put just the organic material, the stuff that contains carbon, in the brackets. And stuff like outside, like the bromide, I kind of leave it out there. But I won't take off if you put it in the brackets. It's okay. Don't worry about that. So now we're in our second step of our mechanism. And in our second step of the mechanism, you have to re-identify what's your new nucleophile and what's your new electrophile. And your new nucleophile here is the bromine. So it's the nucleophile. And this is the electrophile because it's positively charged. So you can see this is positively charged here. The bromine is now bromide, which is negative, so that's nucleophilic. Okay, remember, nucleophiles are electron-rich species. They're Lewis bases. And electrophiles are electron-poor. They're Lewis acids. Okay, it all comes back to Chapter 2. Okay? So if you need to review over Chapter 2, that would be very wise. Okay? So what's going to happen here is that a lone pair is going to come in and attack that carbocation. Go ahead, beat me to it. Try to draw the structure without looking at the answer. I always love it when students kind of go ahead and do everything on their own, figure it out before I finish teaching them, which is always neat to me. The green bonds are the new ones. And then here. The bromine now has 3 lone pairs because one pair turned into bonding, and then there's a hydrogen here. And that's your product here, okay? What you notice is it stays true to the name. This is called electrophilic addition. We added the electrophile across the double bond, okay? It's an addition product. Okay, and that's why I always emphasize to you to learn the actual names of the mechanisms, because I find that it's going to be helpful for you later on. When you're looking at a reaction and you're like, okay, I see it's a double bond, I know it's electrophilic addition, so I need to get the addition product, you know, and it especially helps you when you're doing multiple choice, right? And you're like, oh, that's not an addition product, I don't want that as my answer, cross it off, you know? So it does help to know the name. Now, what are some properties we already know about this particular mechanism? How many steps is it? It's 2 steps, good. Which step is the rate determining step? The slowest step is the first step, excellent. The first step is the rate determining step. We learned that when we talked about thermodynamics and energy diagrams in the last chapter. First step is the rate determining step. And is this reaction spontaneous? Yeah. It's a spontaneous reaction because it has a negative delta G. Right? That's what we're looking for here. So the products are more stable than the reactants. And if I were to ask you to draw the energy diagram, what's on the y-axis? Energy. And the x-axis is reaction progress. The reactants are higher in energy than the products. It's a 2-step mechanism where the first step is the slowest step, so as the largest activation barrier. We make an intermediate, that plateaus there, and then the second step is faster, has a smaller activation barrier. Let's go ahead and label this diagram. These are the reactants, this is the intermediate, and this is the product, right? And the difference between here and here is, here and here, the whole thing, is delta G1 first transition state. And the difference between here and here is delta G2, the second transition state. And the difference between here and the products is delta G with that little degree sign, right? So it's important that you understand how to label your own energy diagrams. This is transition state 1. This is transition state 2. Okay? So we went all over that at the end of chapter 6. So if you need a review over then that'd be a good idea. I derived it for you really quickly here, but it's also really pretty on the next slide. Remember, it's a two-step process. The first transition state is the highest energy point here, has the largest delta G for that transition state. And you can see it's nicely labeled and everything like that that we just did on the previous slide. Okay, so we will derive it on your own. And you don't have to just use hydrogen bromide. So the idea is that I teach you electrophilic addition, and you're able to do it for any starting material that has an alkene and an electrophile such as HCl, HBr, or HI. And that's why I'm working with you right now. In the next chapter, there'll be a whole lot of other electrophiles and mechanisms to work with then. Okay, but they all have similar patterns, so that will be helpful. So I challenge you to practice doing 2-methylpropene on your own with HCl, derive the mechanism, same idea. And I did want to tell you that your reagents here, 1-pentene, to make HI, we have to do a double replacement reaction. So you react potassium iodide plus phosphoric acid to make HI plus potassium phosphate. 3 of those here and 3 of those there to balance it out. So you make it in situ, which means within the reaction. That's why it's kind of in parentheses. You have to make it that way. Now, this is a good point to start talking to you about how to organize your reactions. Now you're learning more reactions. I always organize them based on the type of mechanism. So I'll have like a whole list of electrophilic addition reactions. And I organized it based on reagents and reactants. And then I showed the products, and I gave examples of the products, and I talked about regiochemistry and stereochemistry and any other exceptions to the rule that I should know. So basically, I made tables. A lot of people do flashcards. If that helps you, then that's okay, but be careful with flashcards. A lot of times, students tend to use that as a way to memorize, and then they start drowning when the reactions just pile up, okay? The reason why I think the table is really good because it's still a nice visual. And what I would always do before exams or just practice daily, I would just rewrite my reactions over and over. And then I would challenge myself and say, okay, can I make this alkene look different? Can I add other substituents on it? If I do that, will the reaction still work? Kind of just always thinking outside the box, always kind of challenging yourself as opposed to just using the same starting material that either I provide you or the textbook provides you. You get to be creative here. Make it like a puzzle, okay? And that's where study groups are going to be a huge, helpful, activity for many of you. Because if I come up, or if, let's say I'm in a study group, and if I come up with some good starting materials and I can practice them on my friends, and vice versa, they could test me too with their starting materials, okay? So just letting you know now, be organized. Do not memorize. Like I said, flashcards are not the best. Flashcards are great for vocabulary. They're great, for vocabulary words and stuff like that, but not for reactions. Just letting you know. If you do that, that's your thing, that's fine, but I'm just letting you know. The students I found who do flashcards don't do as well because it's not like a flashcard kind of way to study for this class. Okay, it's more about practicing it. Some of my students carry around whiteboards, just constantly just come up with reactions on their own and practicing problems, so you're not wasting so much paper. So you can do that. Now, you notice when I did my reaction earlier, I was very specific about where the hydrogen of the electrophile added and where the halogen added. And the halogen added to the more substituted side. And electrophilic addition is what we call a regiospecific reaction. Regiospecific means that a particular reactant will go on a specific position. It's not going to go on both. So, for example, here, if we react 1-pentene with hydrochloric acid, we find that 2-chloropentane is the only product we isolate after reacting, not 1-chloropentane. Okay? So we have found that this reaction is regiospecific, and this rule is called Markov-Nakov's rule. Make sure you know how to spell that too. I know it's a hard name, but you can do it. Sound it out. Markov-Nakov's rule. Okay, and you'll find that a lot of reactions and rules are named after the people who discovered them and did the research for it. So it might be difficult at times, but you can do it. Okay? I'm sure if you discover a reaction, you'll name it after yourself too, right? So, why is this? Well, what is the intermediate of your electrophilic addition? We went over this. It's the carbocation. And you can see that right here, that we have carbocations. And the rule of thumb that I've already alluded to and said before is that the more substituted carbocation is more stable. Okay. And so, for example, here, we could either form the carbocation on the first carbon of our double bond or on our second carbon. Now, if we form it on the first carbon, we have a tertiary carbocation. What do we mean by tertiary again? Well, that means the carbon is attached to 3 other carbons, right? Whereas this one here, if we have the carbon or the carbocation on this carbon here, we only have a primary carbocation. So, tertiary carbocations are more stable than secondary carbocations, which are more stable than primary. And I will add on to this rule here later on. There's other types of carbocations like allylic and benzylic. So we'll get to that in later chapters, but for right now it's just going to be based on simple substitution. Tertiary is more stable than secondary, which is more stable than primary. So if your double bond is asymmetrical, you will get the product so that the halogen's on the more substituted carbon because the intermediate's more stable. It'll want to form there. Now you may be like, well, what happens when the double bond has the same kind of substitution on both carbons? And that's going to happen. It's probably not the best way to design a synthesis because, well, I'll tell you why. So when both double bonded carbon atoms have the same substitution, a mixture of products will form. Okay, so if they have the same substitution, then the carbon cation doesn't care where it forms, right? One's not more stable than the other, and so therefore, if you get 2 intermediates, you're going to have 2 products. So be careful with that. You're not always going to have one product for these reactions, and in this next test coming up, you will have a predicting products section. Really think about the ins and outs. Oh, is there an exception to this, or what's different about the starting material? And we'll have some more practice with predicting products together, but what I always have found useful is For example, highlighting the key functional group, like usually using an actual highlighter and highlighting the key functional group. So for example, there's only an alkene here, but later on you're going to add other things, like other functional groups. So adding an alkene and then looking at your reactant and asking yourself, well, is this an electrophile? Is it going to behave as a nucleophile? And then that's how it can help. At least you can start to narrow down your possibilities of how to start the reaction, okay, or the mechanism. I did also want to point out on the previous slide that you did see ether. So over the arrow we show simple reactants, we show solvents, we show temperatures, all sorts of things. We show the conditions to run the reaction, right? And ether is always a solvent. And it may be good for you as you're practicing, you're organizing your list of reactions to also organize a list of solvents. Because eventually you're predicting products that will have multiple reactions happening at the same time. And you need to know, oh, is this behaving as a solvent or is this actually reacting? Okay? Solvents are not supposed to react. And you're going to learn when we talk about ethers, it's really hard to get them to react with anything besides a really strong acid. Okay? And at high temperatures, okay, because you might be like, oh, well, there's strong acid. But I'm talking about, like, really high temperatures. You have to brute force the whole ether thing. So most of the time, ethers are great solvents, okay? And they also make things soluble, which is good. So let's practice a little bit of this here. So let's predict the product of the following reaction. And I suggest that maybe you try doing the mechanism on your own first, because you will be tested on mechanisms. But at least predict the product of the reaction. And when you're done with that, I want you to predict the product or products of this reaction here. Okay. Pause the video, do it on your own, and then come check your work. Well, hopefully you've had a chance to check your work or to do the problem, so you're here only to check your work. No cheating. Okay. So we have the double bond reacting with this here, and we know that halogen is going to go on the more substituted carbon. So you should have had the bromine here. So hopefully you got that as your product. If I ask you to do predicting products on an exam, a lot of times students will always ask me, do I have to show the mechanism or can I show the mechanism? Some people prefer to show the mechanism, and I'm like, please do. You know, all I ask you is that at the very end, you box in your final answer. So you may show a lot, and I usually give you a lot of space so that you can write notes and do mechanisms and stuff like that to help you out. But just box your final answer, okay? And then this one here, how many products did you get? Hopefully you got 2 products. We know the HCl or the halogen, nothing happened to this chiral center here. We know that the halogen will go on the more substituted carbon. So you may have a product that looks like this, but you also may have a product that looks like this. Okay, why is that? Why do we get 2 products? One where the chlorine's on the top face and one where the chlorine's on the bottom face. The reason why you have 2 products is because your intermediate, the carbocation, is sp2 hybridized trigonal planar geometry. Okay? So the reason for 2 products is that carbocation intermediates are sp2 hybridized with trigonal planar geometry. Which means when the chloride attacks the nucleophile, here's your carbocation, it's flat. The chloride can come in from the top face of the carbocation, or it could come in from the bottom face of the carbocation. Okay? So it has equal opportunity to do both. And that's the reason why we get two different products here. You may be thinking, well, what about the first one that we did? Why don't we get two products here? Why don't we get two products here? Is this a chiral center? No. Because it's not a chiral center, we don't have to worry about getting two different products. We don't have chirality. So just be careful with that. So this is not a chiral center. These are. So these are both valid products. Okay? In the next learning check, I'm showing you something a little different. Retrosynthesis. Like the name suggests, that means going backwards. And this is how I'm preparing you for multi-step synthesis. Because at the end of this chapter, and I challenge you, and I hope you will read the little box that's like at the end that talks about organic chemistry and real-world applications. Basically, it talks about natural product synthesis. Because many of you may be thinking, okay, great. If I like organic chemistry and I want to do research, what kind of research is there out there? Well, many organic chemists go into natural product synthesis. Basically, there are a lot of biologists out there who go deep sea diving or go searching through the rainforest for natural products that help to cure diseases. Okay, many of the drugs that you take today that are prescribed by your doctor came from some sort of natural product synthesis. And so then it's the organic chemist's duty to try to synthesize that instead of taking all these like natural products that are from sponges or something like that in the ocean. You know, we're able to make it ourselves. And so you have a structure of a molecule that helps to cure some sort of disease. And you want to design it from really small starting material. And you want to do it as cheap as possible so that the patient, which is you and me, when we go to the doctor and go to the pharmacy, we don't pay so much money, right? They need to be able to mass produce it, right? So it's my goal to train you as, you know, starting out organic chemist to be able to come up with a way to synthesize bigger molecules from smaller starting materials. Okay? So I'm going to start you off now where you're just learning reactions. So your multi-step synthesis will be very basic, coming, you know, like 3-step, multi-step synthesis or something like that. Very basic. And then eventually you're going to, get to like 5, 6, 7-step multi-step synthesis. Some students love it, some students hate it. It's best that you practice it, and we'll have lots of practice together. Once again, having a study group will be really helpful because you guys can come up with your own multi-step synthesis and test one another. Okay? So just letting you know where I'm coming in with this retrosynthesis. Anytime you see like a chunky arrow like this means you're going backwards. That means this is the product, and I'm looking for the reactant or reactants. Okay? Now you only know one reaction here. So when my students start doing multi-step synthesis, and they know a bunch of reactions. Right now you only know one, so this is really easy, but you know a bunch of reactions. I tell them, once again, organize everything. Look at your product and say, what kind of product do I have here? Well, it looks like I have an alkyl halide, where I have like my only functional group here is this halogen. And the only way right now that I know how to make alkyl halides is from electrophilic addition of a double bond. So when you're making your tables, it's good to identify not only an example product, but a generic name for the product. What do we make here? We make a more substituted alkyl halide from this electrophilic addition reaction. Okay, so from electrophilic addition, I know from electrophilic addition that if I want chlorine on it, what kind of reagent do I need to use? I definitely need to use HCl. You can get really fancy and add ether as your solvent. The more you practice adding your solvents in, the better off you'll be. And then you're like, okay, well, I need a double bond, right? And some of you, there's more than one, for this one, there's more than one answer, okay? And that's okay. You know, you choose one route. You can choose the best route, the one that will give you the highest yields. So one way may be that you have the double bond here, right? And then some of you may have put the double bond here, okay? Either way works fine. However, there's one way that might be slightly better than the other. The reason why that is because this carbon here is going to be more like a primary carbocation, and this will be more tertiary, whereas this one will be more secondary and this is more tertiary. So the fact that we have a huge discrepancy between primary and tertiary means that you might have a slightly higher yield of the tertiary product, you know, where the halogen attacks there. But this one would be just as good as well. I have seen students, you know, make another argument and they would say, well, this alkene's not as stable as this alkene here, and that is true as well. So, you know, maybe you won't get as high of a yield because your starting material isn't very stable. So don't worry, I'm not going to get super duper picky as far as like if there are two viable routes, I'll give them both the same credit, and that happens all the time. But, you know, it has to be something that makes sense, that is going to work. So I always will look at your answers and really think about what is it that you were trying to do and try to give you partial credit as much as I can. But show your work. Okay, coming back to the carbocation structure and stability, remember that they are planar. They are tricoordinate sp2 hybridized carbons surrounded by only 6 electrons. So that fourth orbital in the carbon is that vacant p orbital, where it can equally accept a nucleophile from the top or from the bottom. Okay. I already went over this with you. The stability of the carbocation is increased by the presence of alkyl substituents. So it's good to know that trend. It's going to help you out greatly. And why is the reason for this? Well, part of it's due to hyperconjugation, like we talked about earlier, with the talking about the stability of the alkenes, right? So that's why this chapter goes hand in hand with alkenes and carbocations. They're very similar to one another in their stability. Stability comes from hyperconjugation which means that the surrounding orbitals help to stabilize the carbocation. Okay. But another reason, and this is going to be really important, we talked a little bit about it before, I believe in chapter 2, is due to the inductive effect. Okay? And so basically what happens is that the more alkyl groups we have attached to this positively charged carbon, the more electron density, because they're electron donating groups, the more electron density is shifted towards the charge of the carbocation. So it helps to stabilize it. And let me write that down. The more alkyl groups attached to the carbocation, the more electron density shifts towards the charge, and the more inductive stabilization occurs. Okay. And you can see this experimentally looking at the electrostatic potential maps. This methyl cation has no electron donating groups and it is so blue and is so electrophilic, which means it's not very stable. Same thing with a primary carbocation. However, as you start coming with the secondary carbocation, you notice that this helps to localize that carbocation charge. And those electrons are stabilizing it. That carbocations attract it to those electrons that are being donating towards itself. And same thing here. Okay? So a lot of times students at first get confused because they hear me say the electrons want to be spread out. And they do. As you can see here, they want to be kind of spread out here. But this blue spot's not, there's no electrons there. That's the electron poor area, right? So we don't want so much of that. We want that to be more localized, the electron poor carbocation area, okay? And we want those electrons or those alkyl groups to donate electrons towards the carbocation. All right? So both due to hyperconjugation and inductive stabilization. Remember, the inductive effect had to do with electrons being distributed within sigma bonds. Okay? If you don't remember the inductive effect, I would review over it again. Okay? It would be helpful. Now, I finished up the last chapter talking a lot about transition states and that sort of thing. I'm going to do a little bit now again here, kind of finishing up with the Hammond postulate. If the carbocation intermediate is more stable than another, why is the reaction through the more stable one faster? It's a question that you might have. So trying to compare stability of intermediates versus rate of reaction. Remember that the relative stability of the intermediate is related to an equilibrium constant. That's a delta. Delta G. The relative stability of the transition state, which describes the size of the rate constant, is the activation energy. That's delta G with that little funny kind of cross there to help indicate transition state. Remember that the transition state is transient and it cannot be examined. And that there's really, the reason why we have a postulate here, right, like a theory in a sense, is that there's no simple quantitative relationship between the stability of a carbocation and its rate of formation. Okay? There's no simple quantitative relationship between the stability of a carbocation and its rate of formation. And we can't examine its transition state, so we must postulate what it looks like, and that's where the Hammond postulate comes into place. Now, remember that the transition state is the highest energy species in a reaction. By definition, its structure is not stable enough to exist for one vibration for analysis. But we know the structure controls the rate of reaction, so we want to be able to understand what does it look like, so we understand what affects the rate of the reaction, if we can manipulate something to make it faster. So we need to be able to guess about its properties in an informed way. Okay? Make an educated guess, right? We classify them in general ways and look for trends in reactivity, and the conclusions we found are in the Hammond postulate. Basically, the Hammond postulate states that a transition state should be similar to an intermediate that is closest in energy. So sequential states on a reaction path that are close in energy are likely to be close in structure. That's by G.S. Hammond. These are two examples of competing reactions. One where we have the less stable intermediate, which is higher in energy than the more stable intermediate. It went by a slower reaction, and so therefore the more stable intermediate is the faster reaction. This is the most common way that we see happen. But sometimes we may see that a slower reaction produces a more stable intermediate, whereas a faster reaction makes a less stable intermediate. That's not as common, and I'll talk a little bit more about it in detail later, talking about thermodynamic products versus kinetic products. Okay? But what I mean by what does it look like? So for example, coming back to the reaction that electrophilic addition. I've already shown you kind of what the transition state for the first step looks like, right? And the transition state for the first step is an endergonic reaction, right? And because the energy of the transition state is closer to that of the intermediate, we would say the transition state for the intermediate looks, or transition state for the first step looks closest to the structure of the intermediate. Okay? So let me just write that down. Just in general terms, so it makes more sense. Energy, reaction. I'm just going to do single step. So if we have an endergonic, this is the product, and it could be an intermediate. Okay, I'm just doing one step. I know this is a two-step mechanism, but I'm just saying in this one step we have one transition state, right? This transition state here. This is an endergonic reaction. Endergonic, which means the transition state resembles the products. It's because it's closest in energy to the products, right? Whereas if we have an exergonic reaction, and products, and we have the transition state here, this is exergonic, and that transition state resembles the reactants because it's closest in energy to the reactant. So if we know kind of the activation energy and all that stuff, we can kind of it will help us to predict what the transition state looks like. So that's what the Hammond postulate tells us, is that the intermediate, or that wherever the transition state is closest to in energy, is closest to the reactants here, it looks like the reactants. Or if it's closer to the products here in this endergonic reaction, it looks more like the products. Okay, that's what the Hammond postulate helps us to predict. Okay. Okay, the best for last, right? We know we're going through carbocation intermediates, and this can get a little confusing because remember, there are rearrangement reactions. I did talk about that when I gave you an overview of organic reactions. And I said there's addition, there's substitution, there's elimination, and there is rearrangement. And you're like, oh, the rearrangements are always the hardest. But this is actually pretty easy if you practice it. Carbocations do undergo structural rearrangements. They undergo 1,2 hydride shifts. Hydride looks like this. It's a hydrogen with 2 electrons. It's a nucleophilic species. Or 1,2 alkyl shifts. The reason why they will undergo that is because they want to make more stable carbocations. And usually when you have carbocation rearrangements, you will end up getting multiple products. Okay? So let's look at this here. If we had 3-methyl-1-butene reacting with HCl, we find that we get a 50% 2-chloro-3-methylbutane and 50% 2-chloro-2-methylbutane. Why is that happening? Well, a lot of you would do the mechanism and you make the carbocation go on the secondary. Okay, awesome, that works, right? and then you react it with chloride and you make that product. But what we find is that because adjacent to it there's a hydrogen here, that entire hydride comes off, acts as a nucleophile, attacks the carbocation, so we can see the new bond here, and therefore the carbocation is left with a what? Tertiary. Once that happens, the chloride will attack the tertiary carbocation. You can see this is in equilibrium. And we get about a 50-50 mixture here. And the reason why a lot of students just want to give me they get all excited, like, oh, I know there's a carbocation rearrangement here, right? They get super excited, and that's all they give me is that product. But remember, in order to break a bond like that, it requires a lot of energy. So there is a fine balance between having the more stable carbocation and also not requiring so much energy to break bonds, okay? Now, this is really challenging, and we'll practice some more examples in the work session, right? And I'm sure during a review session, maybe we'll practice some more examples. Make sure you understand this particular one I'm showing on the slide from the textbook. But with this one here, you'll notice that that you have to do a 1-2 shift, okay? I don't want to see you pulling off a hydrogen that's like 3 carbons away or even 2 carbons away. It's not going to happen. Okay, it has to be adjacent to it. Okay, you're not going to pull off a hydrogen from far away and it's going to float around and then react. Okay, it must be a 1-2 shift. And if, say, for example, you had a methyl group here, then instead of a hydrogen shift or hydride shift, you'd have a methyl shift. So we do see methyl shifts occur as well. Although, these are not, those are going to happen, but once again, it costs energy and just creates a mixture of products. I think there are some examples in your textbook from the homework where sometimes it'll open a ring up as well, and there might be an alkyl shift to make a 5-membered ring into a 6-membered ring. So crazy things can happen, but as long as you know the mechanism and you understand how hydride shifts happen or how alkyl shifts happen, you'll be fine. But this is a key moment where you're going to have to derive the mechanism itself and not just predict the product. You have to see, can I make a more stable carbocation? So always ask yourself that. Can I do a hydride shift? Can I do a carbocation shift? And I know this is, or can I do a 1-2 alkyl shift to rearrange my carbocation? So I know this is really challenging, and I'm going to practice more with you in person on this, okay? So make sure you're reading through the chapter and you're practicing your homework, and I will be seeing you soon. Take care.